Today we will learn about the multilayer neural networks. So this is the network that is capable to solve the nonlinear problem. So previously you have tested most of the single neuron using four methods: analytical, Hebbian, perceptron, and adaptive linear elements. But that architecture is only capable to solve only for the two-class problem, in which you are given single line, how you're able to spread that thing properly. So if you test the previous exclusive OR problem, you can see that it is impossible in order to get the 100% accuracy. The most you will get is 75%. So this is the introduction of how you're able to solve the nonlinear by using the multi-layer architecture. This is the content of the lecture: introduction, architectures, and the derivation of the backpropagation algorithms. First things, let's revisit this problem. So you are given the exclusive OR problem. So for this particular case, you can actually take the output of the samples. So for this case, if we plot that thing in the scatter plot, so you will have this condition in which the first and then fourth sample will corresponding to the zero target, whereas the second and then third sample will be labeled as the X for this condition. So your aim is to develop a classifier boundary or decision boundary to able to solve this particular problem. So if you have tested previously, let's say we try with a simple neural model, in which for this case we set the threshold to 1.5. So if you try to solve this thing, the possible decision boundary will be y, something like here. So if you try to solve this thing for this problem, so it's quite impossible because of for this decision boundary, let's say this is the boundary for fire, and then this is the non-fire region. So if you use this problem, so the most you will get is 75%. So what will happen if you try to change the different value? So you have the almost the same linear decision boundary and the same situation in which it is impossible for you to solve this problem in order to get a higher accuracy, because of, let's say this is the boundary belongs to the 0 and this is boundary belongs to the 1. So you have another sample here which is 0, that is in the 1 decision boundary. So how we are able to solve this problem? So in a simple way, we need to use the multiple structure of the neuron. So how we solve that thing? So for instance, you will have this first simple neuron in which it will construct first decision boundary of y1 here, and then you stack with the second neuron in the same condition in which we'll have a decision boundary of y2. So you have two neurons that is stacked together, and then later on we need to have some decision maker in order to decide what will happen to this decision boundary. So the final neuron will responsible in order to select region in which, for this case, the final part will be responsible to select either this region. This is, let's say, I label as A, first region, the second region, or the third region here. So this final part will select this region or another region. So how it's done, the selection is based on this concept. So for each of the decision boundary, so let's say I clear the screen. So we have the decision boundary for, let's say, for y1 here, you have this decision boundary. So decision boundary will give two condition, either fire or not fire. Fire means that the region it will the region will belongs to 1, and then not fire will belongs to 0. So this is the same condition will happening for the second decision boundary, which is y2. This is the first one, and then this is the second one. So the final decision boundary, which is y, will select in which region that every decision boundary condition will be overlapped. So I will show you the details by using these samples. We have the same sample here of the exclusive OR. Pick the first sample here, which is the input is 0, 0, and then the target is 0. So once we plug in the input sample, so for the 0, 0, in terms of the first neuron of y1, the input will be 0, since 0 is less than 0.5, so y1 will not fire. So we move on to the second condition for the y2. Input is 0 plus 0. Since 0 is less than 1.5, so we generate the same condition in which y2 will also not fire. So based on the two generated conditions, so the final area that both conditions overlap will be around the same area here, which is in which the 0 sample reside. So to make better understanding, let's fetch the second sample here, which is 0, 1, 1. So for the 0, 1, we first calculate in terms of the y1 condition. So for the y1, your input will be 1. Since 1 is higher than 0.5, so for condition y1 will actually fire up. So for the y2, 0 plus 1 is equal to 1. Since 1 is less than 1.5, so y2 will not fire up. So the same as previous. So we select the region in which the condition overlap. So for this particular case, the center region will be the decision boundary that able to solve this problem. So you can see from here that the sample is accurately located inside of our decision boundary area. For the final sample, which is the sample 110, so if we plug in the value here, so 1, you have 2, since 2 is higher than 0.5, so y1 will be fire up. So for y2, you have input of 2. 2 is higher than 1.5, so for this case y2 will also be fire up. So it will be clearly seen here that since this is the area where both conditions fire up, so we will select the final region in which for this case is accurately tagged where the fault sample target was actually located. So this is a simple illustration on how the things works during the testing phase when you get the information. So basically, this is the whole things regarding the exclusive OR, how we able to use the simple nonlinear model in order to solve the XOR problem. But one of the biggest issues for the multilayer perceptron problem is that how we able to determine the weight, bias, and activation accurately. So this is the information that you need to obtain in order to ensure that your architecture able to solve the given problem. So how we able to get this information accurately? For the simple neuron, we have some simple analytical method, Hebbian, Perceptron, and additive linear element. But for the multi-layer problem, we have an algorithm that we call as the backpropagation algorithm. It's very old algorithm, but it still works up until now. So before we move forward to the backpropagation algorithm, I just want to explain a bit in terms of what is the effect when you select the more complicated architecture. So this is our previous sample that we learned in terms of the single layer. So I've mentioned that we are given the single node, means that we have just single decision boundary. You can use it to solve a very simple linear problem. So the thing that I have just shown you right now is we have the two-layer problem, in which this is the input layer, hidden layer, and then the output layer. So since you have two nodes in the hidden layer, you have two decision boundary. So it can be arranged either in this first condition, second condition, or the third condition. So actually, the third condition supposed to be you will have around three nodes. So moving forward to the more higher complicated. So if you have layer more than two, so for this particular case, you are moving towards the deep learning process. Deep learning means that you have more than one hidden layer. So for this hidden layer, since you have more complicated shape of the neuron, so for this particular case, you will have you can generate more complicated decision boundary in order to solve more complicated problem. So this is some of the example in which the decision boundary was generated in order to separate between these four clusters. So since this is a curved line, so perhaps the activation function is not a simple linear function. Before we move forward to the backpropagation, let's learn a bit about the architecture of our multi-layer perceptron. So usually for the multi-layer perceptron, you will have the input signal and then the output signal. So this is the samples. You can have many samples to be fed to the architectures. So for the linear neuron, which is the input layer, the dimension will be the same as your input signals. If you have, let's say, three dimension of input signals, then your input layer node will be three. So the same thing with the outputs. It will also be depends on what is your dimension of your output sample. However, the one that you need to tune is the hidden layer, which is the center part of this thing. So for every hidden layer, you need to select how much the node that will put to the architecture. It will be depends on your result, so that you will increase or decrease that thing accordingly. For the node, so I just want to re-emphasize on, for every node, we have two parts. The first part, the left part, which is the net, which is sum up everything. And then the right part is the activation function. So if we move forward, if we have more complicated architecture, so this is the deep learning architecture, you just need to increase the hidden layer 1, 2, 3, 4, 5, and etc. So for the node part, we have the activation function. So previously we have used the first one, which is the hard limiter, which is the give the output of 0, 1, and then we have tried with the linear activation function in our adaptive linear model. But there are many activation functions that can be used to feed to your neuron. So most of the popular activation function that used by the deep learning is based on the rectifier linear unit, ReLU. For this derivation process, we will use the sigmoid function. We fed that thing to our architectures, and then we done the derivation by using this sigmoid function. So to understand what is sigmoid function consists of the simple mathematical equation, which is 1 over 1 plus e minus c net j. So c in this case is the parameter that we control how flat is this sigmoid function. So for instance, if you put c more than 1, you will have more steep shape. Whereas if you put a low value of c, you will have more flat shape of the sigmoid function. So from the neural network perspective, if you put if you put the c value lower than 1, so means that let's say c equal to 0.5. So for this case, so what will happening is that you will have much more information retained during the training process, but the training will be longer. So in contrast, when you put C equals to 10, so for this case, the training will be much more faster, but only less information retained during the training process. So there is the pro and cons by select the value. But most of the time we select C equal to 1 during the derivation, and then during for implementation, most of the time we select C equal to 1. So for our algorithm, if you still remember, we will use the backpropagation algorithm in order to find what is the optimal weight, the optimal bias, and then the suitable activation function that can be used for training our models. So basically, this is some history of the backpropagation algorithm. For the learning mode, the thing that you need to know is just what we find is that we try to minimize the error to finding the output, which is our delta W. So if you still remember from my previous class, so for every neural networks model, we want to find the W new. W new will be based on the W old, which is the previous weight of our weight. The previous weight of the model plus delta W, the change of weight. So in our simple neuron, we derive the delta W by using many methods, Bayesian, Perceptron, and etc. For this case, we want to predict the delta W for multilayer perceptron by using the backpropagation algorithm. So the training process will be done in two phases. So the first phase is that we do the forward pass. Forward pass means that you fed the input and then you have the output. So the second part is the backpropagation. Backpropagation means that you have the cost function here. You have the cost function. So the cost function parameters will be backpropagate to the networks in order to determine what is delta W here and then what is the delta W here. So delta W value will be updated for every layer accordingly. In this illustration, I will show you in a simple process what is happening during the training. So it means that for this case, you fed the dogs and then it will be backpropagate to update the weight accordingly. So in the next part, I will show you how we're able to do the derivation process.